In today's class, I'll talk about the spring energy. Spring energy. Now, in previous classes, we did talk about the potential energy, kinetic energy, and the work energy. So if anyone wants to know about them, go and watch the lecture number 1. And this is the lecture number 2. In this, we will, as I said, we'll talk about the spring energy. So if I draw a diagram for the spring, this is how a spring looks like. Now, in this spring, if I try to stretch it in the forward direction, then it has moved a distance of, let's say, x meters. And because of the distance moved x meters, there is certain amount of energy which will be stored in the spring. And that's also called as restoring energy. And the force associated with that is called restoring force. Okay. And restoring energy means the force which you are applying, that's the applied force, and the force which will be stored in the spring once it moves in the forward direction, that will be the restoring force, which wants it to move it back in the opposite direction, and the energy corresponding to that will be restoring energy. Now there are two formulas for the spring energy. One is first one is spring energy formula, that is half kx square, that is spring energy. Es means spring energy. Now k represents stiffness or spring constant. Stiffness or spring constant. This value depends upon the material. It does not change depending upon how much force you are applying or how much you are stretching the spring. So for example, if this is a spring which is made up of, let's say, steel, then you move it in the forward direction and you move it through a distance x meters. And the second time around, if you move this to a x1 meter, it does not mean that k value will change depending upon how much you are moving it. It depends upon the material. If the material of this spring and this spring is same, exactly the same, then k value will always remain the same. So this is the spring energy formula. Now with that, we also need to know about the spring force. And spring force is equal to kx. Again, k represents the spring stiffness or spring constant, and x represents the distance moved. Now, you will see sometimes this force is also written as negative kx. That is equal to restoring force. Again, it's the same. We are applying the Newton's third law. If you apply certain amount of force to move a spring to a distance of delta x in the forward direction, and that force, let's say, is 10 newtons. This is the force applied to move it in the forward direction. Restoring force will be the force which is going to get generated in the spring in the opposite direction. Fr will be equal to negative kx thus. So restoring force in that scenario will be negative 10 newtons. So hopefully you were able to understand the concept of restoring force and the force. Now, based on this concept, I'll try and do a problem, and the problem is in front of us. A spring is stretched. A spring is stretched to a position of 35 centimeter from the equilibrium position. At what point the force exerted on the spring is 10 point. At that point, shall I say, at that point, the force exerted on the spring is 10.5 Newton. What is the elastic potential energy stored in the spring? It's asking us about the elastic potential energy or the spring energy. They mean one and the same thing. Es will be equal to half kx square. Now, half times k value is the spring stiffness given to us. We are not provided with the spring stiffness, so I'm stuck here. Although I'm provided with how much it is stretched. It is stretched to a distance of 35 centimeter. So I'll write it as 0.35 meters. And anyone who doesn't know, 1 meter equal to 100 centimeter. Thus, I've converted this centimeters into a meter format. Now, I need to find the K value. So I'm going to go back and look into the force formula. Force equal to Kx. Is the force provided to me? Yes, the force is provided to me down here. That is 10.5 Newton. Thus, I use this formula. So force is equal to K value, which we are looking for, and force is 10.5 newtons, which is K times X value. X value is given to me, that is 35 centimeters, and which is equal to 0.35 meter. Dividing both sides by 0.35, 0.35, that's gonna give me the K value. So 10.5 divided by 0.35, that will be 30. So K is equal to 30. Now I wanted to find the units of K. So it's very easy to find out the units of K. You don't need to memorize them. Force divided by X equal to K. Force unit is Newton, displacement unit is meter. So K value will be Newton per meter. That's how you represent the K. Now we got this value for K. Now we will put this value of K back into the equation, this equation, and we'll get the answer for spring energy or spring potential energy, whatever you want to call it, half Kx square, half times 30 times 0.35 square. So I'll encourage you to pause the video and do the calculation so that you can match the answer. Your answer should come out to be 1.8375, and the unit of energy is joules. Now we've solved for the part A. I'm going to move to the part B. If the stretch of the spring is allowed to reduce to 20 centimeter, what is the change in the elastic potential energy? So stretch is allowed to reduce to 20 centimeter. So I'm going to redraw the diagram. This is how the spring was. This is initially the spring is, and you stretched it to a distance of 35 centimeter, which is 0.35 meter. And correspond to this point, the energy stored was 1.8375 joules. 75 joules. Now you're gonna release it up to the 20 centimeter of a displacement. So reduce to 20 centimeter of displacement. You are not reducing it by 20 centimeter. You're reducing it to 20 centimeter. So how much you've reduced it? 0.15 meter of relaxation. And this distance is 0.20 meters. Now this begs me the question, how much energy will be correspond to this point? If I can find the energy correspond to this point, and then I will be able to find the difference also, or whatever the question is asking. Spring is stretched to this, what is the change? So it's asking for the change. So now let's find out the energy correspond to the location 2. I'm going to call this location as location 2, this as location 1. At location 2, this will be spring energy will be equal to, again, half kx square, half times k value is 0.2, x value is equal to 0. Oops, this is not 0.2, this is 30, because as we said, spring stiffness does not change. X value is 0.2 square, and if I do the math, 0.2 square multiplied by 30 divided by 2, that's going to give me 0.6. Spring stored energy is equal to 0.6 joules. And now I wanted to find the difference. Difference will come across as change in energy is 1.8 357. Well, I can write it as E final also, E final minus E initial, final minus E initial. That is 0.6 minus 1.8375. 375. So that'll come across as 1.8375 minus 0.6. That is 1.2375 joules delta E. So this is a negative number. Negative only represents that this much energy is lost from the system. Obviously, if you're going to release it, it's going to move in the opposite direction, so the energy is lost from the system. So hopefully you understand now how to approach the spring questions. Make sure you're not making a mistake of just subtracting this displacement and using that displacement of 0.5. Then your answer will be wrong. So what I mean by that, if we're going to use k x2 minus x1 square, or x2 minus x1, which is equal to half k times 0.15, and put it like this, then you will get the wrong answer. Okay, so hopefully that explains you the concepts of spring, and I'll see you with another video. Till then, goodbye.